Hi, my name is John Bredding, and for my BSEE I am focusing in RF. For the Wobbler, I helped design the PID control system and help tune the PID control system, as well as troubleshoot mechanical and software issues.
I'm Jonathan Ariano and I'm pursuing my BSEE. I'm focusing in mechatronics and RF. For the Wobbler, I was in charge of information management, project management, as well as software implementation and design. I was also in charge of the inventory procurement and management, as well as QA for both the software and mechanical side of this project.
My name is Victor Riggle, and I'm pursuing my BSEE with concentrations in RF and embedded systems. And my responsibilities for the Wobbler included the initial design and construction of the wooden base and its components, as well as 3D modeling the system in Fusion 360.
My name is Akeem McCoy, a senior undergraduate electrical engineering student here at the University of South Florida. Today, we will be presenting to you our final project for our electrical engineering design 2 class. Stay tuned.
The main function of the Wobbler will be to actuate a platform so that a ball resting on the same platform will stay at a set point even when the position of the ball is being disturbed by an external force.
This is a 3D model of the Wobbler and its assembly, and we went with a compartmentalized approach. So in the bottom here we have all the power electronics as well as the microcontroller, and in the top compartment we have pretty much everything else, including the servos, the push rods, the center mast and its joint, as well as the resistive panel and the platform it sits on. The initial intention was to 3D print this outside shell, but as time went on we found it more feasible to just construct it out of wood, and that also adds some rigidity into the system and allows for the system to stay stable when these servos are actuating the platform and not allowed to shift around. So this is the inside of the base compartment. We have the power supply, whose voltage is then stepped down by a buck converter, and this buck converter's outputs feed the 2 servos up top as well as the microcontroller over here, which is represented by this green box. We also have 2 inlaid ports on the side, one of which is a USB port that connects to the microcontroller in order to make updates to the code and tune the PID. And we also have an IEC connector that allows us just to plug this into the wall in order to feed the power supply. So the top compartment houses both of the servos, which are supported by 2 columns. The servos then connect to a push rod, and that connects to the bottom of the platform via a Heim joint and a 3D printed joint as well. The center mast also has 3D printed joints to keep it in place, one down here at the base and one up here at the top to support the underside of the platform. There's also a universal joint in the mast in order to allow for these push rods to go up and down, but not allow for the platform to twist around. As for the platform, we have also 3D printed clips to keep the glass resistive panel in place, and that resistive panel has a ribbon cable which can then be fed down into a hole between the compartments. This hole can also serve to feed the power to the servos and the data lines to the microcontroller. So this just allows for direct routing from the microcontroller to the servos to tell them what to adjust and what to do.
For our senior design project, we have built a parallel platform manipulator. It is similar to a Stewart platform. Whereas a Stewart platform has 3 degrees of freedom, our system has 2, allowing for decoupled X and Y axis manipulation. The system is controlled using a PID in each axis with the purpose of keeping a ball at a set point. For this demonstration, our set point is the center of the platform. When we introduce a disturbance to the system, the PIDs will adjust the control servos to respond in kind, such that the ball will be brought back to its set point. A GUI was created to display the internal parameters and measurements of the system. This helped greatly in the tuning and troubleshooting process. The GUI is also a great educational asset as it allows the person tuning the system to observe in real time the positional error, integrator and differentiator outputs, as well as the total PID output. The display also shows the position of the ball in an entertaining manner. So as you can see, the ball is disturbed and comes right back to the center. And if you look at the PID viewer that we have set up over here, you can see where the ball is relative to its X and Y position. Over here we can see in these top graphs right here, we have the X error and the Y error. We have the PID output for the X and the PID output for the Y. We show the change in angle for both the X and Y, Here we have the integrator output, but for this system we're not using the integrator as it ended up causing more oscillation. Lastly, we have the differentiator output. So if you look at the outputs, you can see how they change relative to that impulse. Our original intention was to design and utilize a capacitive sensor array, but the initial design could not provide dependable feedback, and it was determined that further research and development would be needed. We concluded that we did not have enough time to fulfill our self-imposed requirement, and compromised by using a resistive touch panel normally found on a point-of-sale system. For the servos, we are using off-the-shelf, high-tech D645MW hobby servos. They are running at 6.3 volts and with a specified torque of 12.9 kilograms per centimeter. For the microcontroller, we are using an STM32G4074RE Nucleo board running at 170 megahertz. The board was selected due to its operating frequency, 512 kilobyte flash memory, and numerous onboard peripherals and timers. For this demonstration, we will show that the system can also move the set point based on a predefined pattern. To achieve this, the positional area of the ball is compared to a set range. When the ball settles in that range for a number of counts, the set position of the PID is changed to the next point of the pattern. The system will still respond to external disturbances during its movement through the pattern, as we can see here. And then once it settles, it'll move back to the next point. Unfortunately, the resistive panel is prone to noise and sporadic measurements. We are using numerous filtering techniques to reduce the impact of noise. These include debouncing the touch measurements, using a running median filter to remove outliers, using a sampled moving average during differentiation, and bounding the recorded measurements relative to a delta from the previous measurement. With the larger ball that we are using, a majority of this noise is not present due to more consistent contact with the panel. But if we use a lighter ball, we can see the impact of this noise in the response.